Hey AP Stats, we're going to talk about Chapter 7 today. And Chapter 7 is still dealing with probability ideas. We're just going to kind of narrow it down to very specific types of probability. And what we're going to be talking about, the whole chapter, you can see, is random variables. That's the key to this. So a random variable is a variable whose value is a numerical outcome of a random phenomenon. Another definition is a numerical value whose value depends on the outcome of a chance experiment. Usually random variables are denoted by capital letters such as X or Y. And a lot of times we end up using variables near the end of the alphabet. I don't know why, just kind of the way it is. The random variables are either discrete or continuous. So a random variable that is discrete has a set of possible values in a collection that are isolated points. Okay, on the number line. Or something, usually it's called like a countable number of things. So in practice, discrete random variables almost always arise in connection with counting. They don't have to necessarily be whole numbers, but we're usually like landing on specific values. So the number of items purchased, the number of eggs broken in a carton, the number of gas pumps in use, those all are like a countable number of things. And they don't go on to infinity, like you're just looking at a certain set. Okay, so a random variable that is continuous, if its set of possible values include an entire interval. Continuous random variables are one whose values are typically obtained by measurement. Okay, so the temperature in a freezer compartment. We are only limited by our measuring device. If it's 1 decimal place versus if it's 2 or 3, we can have continuous values, which means all the possible decimals between, in the freezer, I don't know, if it's, 20 degrees to 32 degrees or something like that. Like we can just have all possible values in between there. So a lot of times it occurs with measurement, like height, weight, weight of a pineapple, amount of time spent in the store. Those things that were only limited by our measuring device. Okay. So possible values for a discrete random variable, they're usually like isolated points that are countable. Possible values for a continuous random variable take up that whole interval. Okay. So determine if each of the following random variables is continuous or discrete. So the number of defective tires on a car, that's going to be discrete. I'm just going to put a D for discrete. Body temperature of a hospital patient, that's going to be continuous, okay? Because it's going to go over that whole interval. The number of pages in a book, that is discrete. That's like a countable number of things. Even though there are lots of possible values, it's still like a countable number of pages. A lifetime of a light bulb, that's going to be continuous. Okay. So we're going to split these up throughout this chapter and talk about certain things for discrete and then continuous. So the first one we're going to talk about is discrete. So a discrete random variable, x, has a countable number of possible values, and then the probability distribution of the discrete random variable lists the values and then the probabilities. So a lot of times we're going to see this in a table. So the probabilities must satisfy 2 requirements. Obviously, every probability is between 0 and 1. That's true of all probabilities. But then the sum of the probabilities is 1. So we have to account for all possibilities here in the table. All right, so a consumer organization that evaluates new automobiles customarily reports the number of major defects on each car examined. A large number of automobiles were evaluated, and the probability distribution consistent with these observations is below. Let X denote the number of major defects on a randomly selected car of a certain type. So defects range from 0 to 10. And if you look at the probabilities, can you tell where these tend to, like most often, how many defects does it appear to be? Can you tell based on those probabilities? Like for example, 10 is very small. 10 defects is small, so is also 0. So I would say most of them range, just so we have an idea about this, like 2 to 6, or really like 2 to 5 kind of is where we see most of our defects occurring, most likely. Okay, so we're just going to be asked some questions about this. So find the probability that there are more than 5 major defects. So we're still going to be using probability notation. Probability X is greater than 5. And in the table, we're just going to sum up like 6 through 10. So 0.091 plus 0.046. So just grab your calculator and sum these guys up. And you can see it's still not very likely to have 6, 7, 8, 9 defects. So this probability is probably still on the smaller side. Okay, so you should get 0.161. Okay. So find the probability the number of major defects is between 2 and 5 inclusive. What does inclusive mean? It means we're including 2 and 5. So we're going to do 2 to 5, but we're including them. So, oh, that's the interval that I already boxed off. So 0.209, 223, 188, 114. So again, just grab your calculator. We're just going to add those up. And we should get 0.734. Okay, C, at most 3 major defects. So we want probability notation at most is going to be less than or equal to 3. So we're adding up the 0, the 1, the 2, and the 3. So we add those, we should get 0.537. Okay, consider tossing a coin 5 times. What is the probability distribution of a discrete random variable x that counts the number of heads in 5 tosses of a coin? So we have a problem that's very similar to this, and we'll kind of see some problems like this as we go through this chapter, but this is very much like a test problem that you have. But it'll kind of combine this as well as binomial from next chapter. So tossing a coin, we're looking at x is the number of heads. That's what we're looking at in 5 tosses of a coin. So what are the possible values of x? If we toss the coin 5 times, what are the number of heads that I can get out of there? We can have 1, 2, 3, 4, 5, and don't forget 0. I feel like a lot of students end up forgetting 0. So we can have 0, 1, 2, 3, 4, or 5 heads. Okay, so these are the number of heads. And then we want to figure out the probability. So there's a couple ways that we're going to deal with this. This really is a binomial problem, but I'm going to try to get through it without having to show you all the binomial. The binomial makes it easier. But if we're going to toss a coin 5 times, that means that 1, 2, 3, 4, 5. We have 5 slots. We have 2 options, a head or a tail for each one. So my total number of options is 2 to the 5th, which is 32. So how many of them are going to have a case where I have 0 heads? It only happens once, okay? Same with 5. So those are both, I'm going to write these as decimals, but these are 1 out of 32. So the decimal conversion of that is 0.03125. Okay, so now we want to write out the number of ways that we can get 1 heads in any order, 2, 3, 4, etc. So does anybody know a way that you've probably heard of that will tell you that pattern? Has anybody heard of Pascal's triangle? This also deals with, you can do this as a combination as well. I'm just not going to teach that way to you yet until we talk about binomial. But Pascal's triangle, it looks like this. And then there's always ones on each side, and then you sum up the numbers above it. So 1 and 1 would be 2, 1. So we're going to do this again. These would be 3, 3, 1. And we're going to keep going until we get to the 5th row, because we're talking about doing this 5 times. So because we're tossing a coin 5 times, we're on the 5th row. So do you see that this is the number of heads that we got? 0 heads was one way, and then the number of heads that we have 5 was one way. So here, for this one, is saying the number of ways that we can have one head in there. If we wrote all these out, it would be 5 out of 32. The next one would be 10 out of 32, 10 out of 32, and 5 out of 32. We will talk a lot more about this type of setting up this type of probability. So don't let this get stump you at this point. This, I'm just going to write these as decimals, 0.15625, and then these ones are 0.3125. Okay. So that is how we're going to set this up. We're going to draw a probability histogram for this. So x is going to be down here, and I'm going to have my 0, 1, 2, 3, 4, 5. My 0.3125, split that in half, which is actually 0.15625. And then draw this. So 0 is pretty small. It's down here. 1. So we're going to just draw this as a histogram. Histogram, the bars touch. Oops, it should be the same height. Sorry. Okay. So that's just the probability histogram. It's most likely that you will get a 2 or 3 heads when you toss the coin 5 times. Okay. We're going to use our table to find the probability of tossing at most 2 heads. So that's less than or equal to 2. So we're going to add up 0, 1, and 2. Okay, so any idea on what that would turn out to be? It'll come out to be 0.5. Okay, so here we're going to start to see this question. We saw it a little bit last chapter, and so probability of tossing at least 1 head. So x is greater than or equal to 1. So you can add up 1, 2, 3, 4, 5. Or since we know our probability sum to 1, we can still do the same strategy and do 1 minus the probability x equals 0. You'll get the exact same answer either way, so that's 0.03125. So you can add up 1 through 5 or just subtract off the one that we're not considering, and you'll get 0.96875. You get the exact same answer either way. Okay, so that's a little discrete probability distributions. You're definitely going to be using a table to look at those countable number of probabilities. So with a continuous random variable, so we're going to talk about continuous. X takes values, all the values, in an interval, okay, of numbers. The probability distribution of X is described by a density curve. Okay, hopefully bells are going off in your head because we've talked about density curves before. So we're at the very cusp of starting to go back and use a lot of information that we've already seen before. This is kind of like this chapter is where we start to use it. The probability of an event is the area under the density curve. Okay, so now hopefully you're really figuring this out. How do we find the area under curves? Do you remember this? Hopefully. We started talking about z-scores, normal CDF. That's how these all tie together. Okay, so all continuous probability distributions assign a probability of 0 to every individual outcome. Okay, so highlight this. we will come back to this and kind of talk about this a lot. So the reason is because we are now talking about area. You know, like if I'm looking at area of a rectangle, what's the area of just a line? Just a line. There is no area, because the area, you need a length times a width to be able to find that. So each individual outcome actually has the probability of 0. We need an interval to go between two values so that we have a length and a width, basically, to figure that out. Okay, so only intervals of values have positive probabilities. So this is why when for continuous, this is big, for continuous, it doesn't matter if you do less than or like less than or equal to, because every individual value, the probability is 0. In the last one we were talking about, though, like in discrete, if I pop back up here, does each individual value have a probability? Yes, it very much matters if we have a less than or equal to or just a less than. So this only applies to continuous, for continuous, okay, big thing, only for continuous. So all density curves have areas that are exactly 1 and do not go below the x-axis, so it's 0 and positive. Density curves can be any shape, so this one is kind of like a funky one. We'll also see some that are like uniform, so it's going to be straight across. But a normal curve is a specific type of density curve. So these fit within this, and we have a mean and a standard deviation, and we're going to find z-scores. Okay, so that's another way to solve these. So consider the random number generator on your calculator. If we allow it to generate a long sequence of numbers between 0 and 1, it will spread it out uniformly across the entire interval. So uniform means that it doesn't like peak in the middle. They're all equally likely, so it's straight across. Okay, so we know the area has to equal 1, so that's how we know this base times the height would be 1. There's other problems where this is unknown and you have to find it. So again, remember that like the base times the height has to equal 1 if you have to find that. But this one is 1. So okay, so for A, we want to just look at 0.36. I'm just going to approximate that. 0.36 and less than, so this side. So we're just looking at this base times the height. So all our heights here, though, are 1. So the area here is just going to be 0.36. Can I determine that A and B are slightly different? No. They are exactly the same. There's no difference between using a less than or equal to. Okay, exactly the same. For greater than 0.47, so for this one, we're going to change this up to 0.47. Use this guy. So you can just figure out the values that are greater than 0.47, or you could do 1 minus 0.47, whatever you like. But you're going to get 0.53. Okay, the difference between 0.14 and 0.83, do we know what that is? Yep, 0.69. These are all the same because we're multiplying by a height of 1. Okay, and then for E, we're doing 2 cases, so less than 0.21 or greater than 0.68. So they don't overlap. Like if we think about our probability, there's just one case or the other case. So less than, oh my goodness. So less than 0.21, sorry, technical difficulties, I don't know what's going on, is 0.21, and then or, so we're going to add what's greater than 0.68. Yep, 0.32, so add those two situations together, get 0.53. And then probability x equals 1 value. So what is that? If I just graph this on here, if I just want 0.72, it just equals 0.72. Is there any area to that? No, there's no area, so this is 0.